Welcome to Earthly Teachings, where learning is clear and powerful. Today, we are working on Mathematics N6, focusing on a crucial topic, calculating the area bounded by curves. This is a fundamental application of integral calculus. In this video, we'll walk through several problems step by step, explaining the logic behind every decision. You will learn to: first, sketch the region of interest. Second, set up the correct definite integral, which involves identifying the upper and lower functions. And third, solve the integral to find the area. It's important to understand the concept and not just memorize formulas, so let's learn together. We'll start with our first question from Activity 5.1. Our first problem is to calculate the area bounded by the curves. X equals 4 minus y squared, x equals y squared, and y equals 0 in the first quadrant. The equations we're working with are x equals 4 minus y squared, x equals y squared, and the boundary line y equals 0. The region is in the first quadrant. Notice here that the equations are given in terms of x as a function of y. This tells us it will be much easier to integrate with respect to y. The general formula for area when integrating with respect to y is the integral from c to d of the rightmost function minus the leftmost function. Our first step is always to sketch the region. This helps us see which function is on the right and which is on the left, and where the curves intersect. The first curve, x equals 4 minus y squared, is a parabola that opens to the left. It crosses the x-axis when y is plus or minus 2. The second curve, x equals y squared, is a parabola that opens to the right. It passes through the origin. The problem also specifies y equals 0, which is the x-axis, and the first quadrant, meaning y must be positive. This already starts to define our region. Let's highlight our boundaries. We have the x-axis, the parabola x equals y squared, and the parabola x equals 4 minus y squared. Now we need to find the points of intersection to determine our limits of integration, c and d. We find where the two parabolas meet. We set the two x equations equal to each other. 4 minus y squared equals y squared. Adding y squared to both sides gives 4 equals 2y squared. Dividing by 2, we get 2 equals y squared. So y equals the square root of 2 since we are in the first quadrant where y is positive. To find the x-coordinate of the intersection, we can substitute this y value into either equation. Using x equals y squared, we get x equals 2. The intersection point is therefore 2 square root of 2. Let's label this on our sketch. This point is crucial because it splits our region. Looking at our sketch, from y equals 0 to y equals square root of 2, the curve on the right is x equals 4 minus y squared, and the curve on the left is x equals y squared. This means our integral for the area will be the integral from 0 to square root of 2 of 4 minus y squared with respect to y. Now, let's simplify the integrand before we integrate. The integrand simplifies to 4 minus 2y squared. This makes the integration process much simpler. Let's integrate this term by term. The integral of 4 with respect to y is 4y. The integral of 2y squared is 2y cubed over 3. We evaluate this from 0 to square root of 2. Now we apply the fundamental theorem of calculus. Plug in the upper limit and subtract the result from plugging in the lower limit. Substituting square root of 2 gives 4 times square root of 2 minus 2 times square root of 2 cubed, all over 3. Plugging in 0 gives 0. Let's simplify the term square root of 2 cubed. Square root of 2 cubed is the square root of 2 times the square root of 2 times the square root of 2, which equals 2 times the square root of 2. So we have 2 times that, which is 4 times the square root of 2. Our expression for the area becomes 4 square root of 2 minus 4 square root of 2 over 3. To combine these, we find a common denominator, which is 3. 4 square root of 2 is the same as 12 square root of 2 over 3. Subtracting 4 square root of 2 over 3 gives 8 square root of 2 over 3. The final exact answer for the area is 8 square root of 2 over 3. If we round to 3 decimal places, we get approximately 3.771 square units. A common mistake to avoid in problems like this is integrating with respect to x. If we had tried that, we would have had to split the integral into 2 parts, which is much more complex. Always choose the path that simplifies the integration. To recap, we successfully calculated the area by integrating with respect to y, which was the simpler method. We sketched the graphs, found the intersection point, identified the right and left functions, and performed the integration. Let's move on to our next problem. We need to calculate the area bounded by the exponential function y equals e to the x, the natural logarithm function y equals ln of x, and the vertical lines x equals 1 and x equals 2. This time, both functions are written as y equals a function of x. This tells us we should integrate with respect to x. The general formula for area with respect to x is the integral from a to b of the upper function minus the lower function. Let's sketch the graphs to visualize the area. The graph of y equals e to the x is a classic exponential curve, always positive. The graph of y equals ln of x is the inverse, which is symmetric about the line y equals x. The problem gives us vertical lines x equals 1 and x equals 2. These are our limits of integration. The area we are interested in is the region between the two curves from x equals 1 to x equals 2. From our sketch, it's clear that the exponential function e to the x is above the natural logarithm function ln of x in this interval. So, our upper function is y equals e to the x, and our lower function is y equals ln of x. Our limits are a equals 1 and b equals 2. We can now set up the integral. The area is the integral from 1 to 2 of e to the x minus ln of x with respect to x. To solve this, we can split it into two separate integrals. This gives us the integral of e to the x from 1 to 2 minus the integral of ln of x from 1 to 2. The integral of e to the x is just e to the x. The integral of ln of x is a standard result that we should know or derive using integration by parts. It's x ln of x minus x. So, the antiderivative of our integrand is e to the x minus the quantity x ln of x minus x. Now we evaluate this from 1 to 2. Plugging in the upper limit 2 gives e squared minus the quantity 2 ln of 2 minus 2. Plugging in the lower limit 1 gives e to the first power minus the quantity 1 ln of 1 minus 1. Let's simplify this. The natural logarithm of 1 is 0, so the term in the second bracket simplifies to e minus 1. The expression becomes e squared minus 2 ln 2 plus 2 minus the quantity e minus 1. Distributing the negative sign, we get e squared minus 2 ln 2 plus 2 minus e plus 1. Combining the constants, we get our exact answer, e squared minus e minus 2 ln 2 plus 3. For the final numerical answer, we'll use a calculator. E squared is approximately 7.389. E is approximately 2.718. ln of 2 is approximately 0.693. Plugging these in, we get approximately 7.389 minus 2.718 minus 1.386 plus 3, which equals 6.285. Rounding to 3 decimal places, our area is 6.285 square units. In this problem, we saw how to integrate a difference of functions with respect to x. The key was correctly identifying the upper and lower functions based on our sketch. Let's tackle the next area problem. We need to calculate the area bounded by the curve y equals ln of x, the x-axis, and the horizontal line y equals 2 and the vertical line x equals 0. The first thing we should always do is sketch the graphs to see the region we need to integrate. We'll draw our coordinate plane. The graph of y equals ln of x passes through the point 1, 0 and extends upwards to the right. The problem gives us 3 boundary lines. First, y equals 0 is the x-axis. Second, y equals 2 is a horizontal line. And third, x equals 0 is the y-axis. Now let's highlight the area that is enclosed by all 4 of these boundaries. Notice that the curve y equals ln of x is on the left side of this region. The area is enclosed by y equals ln of x, the y-axis, the x-axis, and the line y equals 2. Because the region is bounded by a curve on the left and a vertical line on the right, it will be easier to integrate with respect to y. Our limits for y are given in the problem as 0 and 2. So we will be integrating from y equals 0 to y equals 2. To do this, we need our equations in the form x equals a function of y. The line x equals 0 is already in this form, but our main curve is y equals ln of x. We need to rewrite this. Recall the definition of a logarithm. Y equals ln of x is equivalent to x equals e to the power of y. This is our leftmost function. x left. So our leftmost function is x equals e to the y. What about the rightmost function? X right? Looking at our sketch, the right boundary of the shaded area is the y-axis, which has the equation x equals 0. However, wait, the problem statement gives x and 0 as a boundary. The region described by y lnx, y equals 0, y equals 2x is 0, is the part of the region we've drawn that is between y is 0 and y is 2. Let's re-examine the graph. If we go from x to 0, the y-axis, to y lnx, that isn't an enclosed area as it isn't bounded to the right. Let's look at the wording carefully. The wording is y equals ln and x, y equals 0, y equals 2, and x equals 0. This implies an area bounded to the left by ln x and to the right by x is 0. But ln x only exists for x arrow. The intersection of y ln x and x separ 0 doesn't happen. It seems more likely the question intends for the area to be bounded between y ln x and the y-axis, over the interval from y at 0 to y are 2. Let's work with the interpretation that the y-axis is the right boundary, meaning x right equals 0. This would result in a negative area, as e to the y is always positive. A negative area doesn't make physical sense. This suggests a common trap for students. When you get a negative area, it means your upper and lower functions were chosen incorrectly, or, as in this case, the right and left functions. It's almost always the case that you are integrating the absolute value of a function, or the rightmost minus the leftmost. If the region is to the left of the y-axis and right of x y, then x's right is 0 and x's left is ei. Let's check the result with this setup. The integral would be from 0 to 2 of 0 minus e to the y dei. This gives e to the y from 0 to 2, which is negative 6.389. As expected, a negative area. It's highly probable the question meant the area between y equals ln of x and the y-axis, from y equals 0 to y equals 2. In this case, the rightmost boundary is y equals ln of x, which we rewrite as x equals e to the y, and the leftmost boundary is the y-axis, or x equals 0. Let's assume this was the intended problem. In an exam, if you encounter such ambiguity, state your assumption clearly. So we'll assume x right is e to the y and x left is 0. Our integral becomes the integral from 0 to 2 of e to the y minus 0 di. The integral of e to the y is simply e to the y. So we have e to the y evaluated from 0 to 2. This gives us e squared minus e to the power of 0. Remember that any number to the power of 0 is 1. So the area is e squared minus 1. Calculating this, e squared minus 1 is approximately 6.389 square units. This is a positive area, which makes physical sense. Let's quickly check this. The original wording, if interpreted literally, describes the region to the left of the y-axis. But the function y ln x only exists for x0. The region we calculated is to the right of the y-axis. The confusion is over the x0 boundary. Often, bounded by x0 just means the y-axis serves as one of the enclosure lines. The positive area we found is the logical one for an exam question. Always visualize and ask yourself if your answer makes sense. Next up is a trigonometric area problem. We need to find the area between the graphs of y equals 2 sin x and y equals sin x over the interval from x equals 0 to x equals pi. Again, our first and most important step is to sketch these graphs within the given interval. Both graphs are sine waves. Y equals sin x starts at 0, peaks at 1 at pi over 2, and returns to 0 at pi. The graph of y equals 2 sin x is a vertical stretch of the first graph by a factor of 2. It peaks at 2 at pi over 2. So here are our two sine waves over the interval. The area we want is the space between them. From our sketch, it's clear which function is the upper boundary and which is the lower boundary. The graph y equals 2 sin x is always above the graph y equals sin x in this interval. So 2 sin x is our upper function, and sin x is our lower function. The limits of integration are given directly in the problem, from x equals 0 to x equals pi. So we can set up our integral. The area is the integral from 0 to pi of the upper function minus the lower function. That's the integral of 2 sin x minus sin x dx. Let's simplify the integrand before we integrate. 2 sin x minus sin x is simply sin x. This makes the integral very straightforward. The integral of sin x is a standard result. The integral of sin x with respect to x is negative cos x. So we evaluate negative cos x from 0 to pi. Now we plug in the limits. Be very careful with the signs here. The area is negative cos of pi minus negative cos of 0. This simplifies to negative cos of pi plus cos of 0. Let's recall the values of cosine at these points. The cosine of pi is negative 1. The cosine of 0 is 1. Substituting these values, we get area equals negative 1 plus 1. This gives us 1 plus 1, which equals 2. The area between the two sine curves is exactly 2 square units. The exact and rounded answer are the same. A common mistake here would be to forget the negative sign from integrating sin x, or to evaluate cos 0 and cos up incorrectly. A quick visual check confirms our answer. The area under a single arch of sin x is 2. We're effectively finding the area under 2 sin x and subtracting the area under sin x, which leaves the area under one arch of sin x. So we successfully found the area by sketching the functions, identifying the upper and lower functions, setting up the integral, and carefully evaluating the trigonometric function at the limits. Our final area problem for this module. We need to calculate the area bounded by the curves y equals e to the x, y equals e to the 2x, and the vertical line x equals 2. As always, the sketch is our starting point. Let's see what these graphs look like. Both are exponential growth functions that pass through the point 0, 1. The graph y equals e to the 2x grows much faster than y equals e to the x. The given boundary is x equals 2. The area we need to find is bounded by these three curves. It's the region between the two exponential curves, from x equals 0 to x equals 2. Looking at our sketch, it's clear that the upper function is y equals e to the 2x, and the lower function is y equals e to the x. Our limits of integration a and b aren't fully given. We have the upper limit x equals 2, but what is the lower limit? In cases like this, where a boundary isn't explicitly given as x equals a constant, it's usually implied that the lower limit is the point where the two curves first meet. Let's find the intersection point by setting e to the x equal to e to the 2x. To solve for x, we can take the natural logarithm of both sides. This is a common and effective strategy. The natural log of e to the x is x. The natural log of e to the 2x is 2x. This gives us the simple equation x equals 2x. The only solution is x equals 0, so our lower limit of integration is 0. So we are integrating from x equals 0 to x equals 2. The integral for the area is the integral from 0 to 2 of the upper function e to the 2x minus the lower function e to the x. Let's find the antiderivatives. The integral of e to the x is e to the x. The integral of e to the 2x requires a u substitution, but a quick rule to remember is it's e to the 2x divided by 2. This gives us our antiderivative. Now we evaluate this from our limits, 0 and 2. We plug in 2, then subtract the result of plugging in 0. Let's simplify this. Remember, e to the power of 0 is 1. The expression becomes 1/2 e to the 4th minus e squared, minus the quantity 1/2 minus 1. Simplifying the last part, minus negative 1/2 becomes plus 1/2. So our exact answer is 1/2 e to the 4th minus e squared plus 1/2. Let's calculate the numerical value, rounded to 3 decimal places. E to the 4th is about 54.6. E squared is about 7.389. Half of 54.6 is 27.3. So we have 27.3 minus 7.389 plus 0.5, which gives us an area of approximately 2411 square units. A common mistake here would be to assume the lower limit is 0 without solving for it. While it turned out to be 0 in this case, always solve for intersection points to find the correct limits. Now we move on to question 2. This question is a 3-part problem. Determine intersection points, sketch the graphs, and calculate the area bounded by them. Let's start with part 2.1. Determine the points of intersection of y equals x squared plus 2 and y equals x plus 4. To find where two curves intersect, we set their y values equal to each other. This gives us a quadratic equation. To solve it, we need to set it to 0. Subtracting x and 4 from both sides, we get x squared minus x minus 2 equals 0. This quadratic factors nicely. We need two numbers that multiply to y2 and add to 1. Those are 2 and plus 1. So the factored form is x minus 2 times x plus 1 equals 0. This gives us two x coordinates for our intersection points. X equals 2 or x equals 1. To get the full coordinates, we must find the corresponding y values by plugging these x values into either of the original equations. The line y equals x plus 4 is simpler. For x equals 2, y is 2 plus 4, which is 6. For x equals 1, y is 1 plus 4, which is 3. So the two graphs intersect at the points 2, 6, and 1, 3. These points will serve as our limits for integration later. Now for part 2.2, sketch the graphs. I equals x squared plus 2 is an upward opening parabola with its vertex at the y-axis at the point 0, 2. Y equals x plus 4 is a straight line with a y-intercept of 4 and a gradient of 1. Let's draw these on the same axis. The parabola has its vertex at 0, 2. The line goes through 0, 4, and as we just calculated, they cross at 2, 6 and 1, 3. Labeling these points and the intersection points makes our sketch clear and accurate. Finally, part 2.3. Calculate the area bounded by the graphs. The bounded area is the region between the line and the parabola. This is an area with respect to x. Our lower limit, a, is the leftmost x-coordinate of intersection, which is 1. Our upper limit, b, is the rightmost x-coordinate, which is 2. From the sketch, it's very clear that the line y equals x plus 4 is the upper function, and the parabola y equals x squared plus 2 is the lower function. The area is the integral from a 1 to 2 of the upper function, x plus 4, minus the lower function, ax squared plus 2. Let's simplify the integrand before integrating. Distributing the negative sign gives x plus 4 minus x squared minus 2. Combining like terms, we get x squared plus x plus 2. Now we integrate this polynomial term by term. The integral is negative x cubed over 3 plus x squared over 2 plus 2x. We evaluate this from 1 to 2. This is where students often make calculation errors. Be careful with the signs. Plugging in the upper limit 2 gives negative 8 over 3 plus 2 plus 4. Plugging in the lower limit 1 gives positive 1 over 3 plus 1/2 minus 2. Simplifying, we have negative 8 over 3 plus 6 minus the quantity 1/3 plus 1/2 minus 2. Let's find a common denominator for each bracket. For the first one, it's 3. For the second, it's 6. This gives us negative 8 plus 18 all over 3 minus the quantity 2 plus 3 minus 12 all over 6. Simplifying further, we have 10 over 3 minus negative 7 over 6. This becomes 10 over 3 plus 7 over 6. To add these fractions, we need a common denominator of 6. 10 over 3 is the same as 20 over 6. So we have 20 over 6 plus 7 over 6, which equals 7 over 6. This fraction simplifies to 9 over 2, or 4 and 5. The area is 4 and 5 square units. In this multi-part question, the careful and ordered steps led us to the correct answer. We started with the intersection, used it for the sketch and the limits, and then accurately set up and evaluated the integral. We've arrived at the final question in our activity. Question 3 also has two parts. Sketch the graphs of a circle and a line, and then calculate the area between them in the first quadrant over a specific x interval. Let's begin with part 3.1. Sketch the graphs of x squared plus y squared equals 9 and y equals 2 minus x. First, consider the equation x squared plus y squared equals 9. This is the standard form of a circle centered at the origin with a radius of the square root of 9, which is 3. Second, y equals 2 minus x is a straight line with a y-intercept of 2 and a negative gradient of 1. Let's draw these. The circle is centered at the origin. The line passes through 0, 2, and 2, 0. Now for part 3.2. Calculate the area between the graphs in the first quadrant from x equals 0 to x equals 2. We are looking at the first quadrant, so we only need the top part of the circle. We are integrating from x equals 0, the y-axis, to x equals 2, a vertical line. The area we need to calculate is the region bounded by the line, the x-axis, the vertical line x plus 2, and the quarter circle. This isn't bounded between the curves in the way we usually calculate. Let's reinterpret this. It's more likely we need to find the area under the circle and subtract the area under the line in this interval. From our sketch, the upper curve is the circle and the lower curve is the line. We need to express the circle's equation for y. Since we're in the first quadrant where y is positive, we take the positive square root. So y equals the square root of 9 minus x squared is our upper function. The lower function is y equals 2 minus x. The limits of integration are explicitly given. A equals 0 and b equals 2. So, our integral is from 0 to 2 of the square root of 9 minus x squared, minus the quantity 2 minus x dx. This is where it gets interesting. We have two parts to this integral. The first part is the integral of the square root of 9 minus x squared. This is a special integral. The second part is the integral of the polynomial. Let's focus on the first part, the integral of the circle function. This integral, the square root of a squared minus x squared, is the formula for the area of a sector of a circle. Here, a squared is 9, so a is 3. The antiderivative is x over 2 times the square root of 9 minus x squared, plus 9 over 2 times the inverse sine of x over 3. A common mistake here would be to try to use a substitution or to assume it's simple. Recognizing this as the circle formula is key. Now let's find the antiderivative for the second part. The integral of 2 minus x is 2x minus x squared over 2. Combining them, our complete antiderivative is x over 2 root 9 minus x squared plus 9 over 2 arcsin x over 3 minus the quantity 2x minus x squared over 2. Now we plug in our limits, 0 and 2. The whole expression evaluated at 0 is 0. So we only need to evaluate it at the upper limit, x equals 2. Substituting 2 into the first part, we get 2 over 2 times the square root of 9 minus 4, plus 9 over 2 times the inverse sine of 2 over 3. This simplifies to the square root of 5 plus 9 over 2 arcs in 2, 3. Now for the second part at x equals 2. We get 2 times 2 minus 2 squared over 2. That's 4 minus 4 over 2, which is 4 minus 2, or 2. Combining these, the exact area is the square root of 5 plus 9 over 2 times arcsin 2, 3 minus 2. Let's get the numerical answer. Remember that arcsin should be calculated in radians. The square root of 5 is about 2.236. Arcsin 2, 3 is about 0.7297 radians. 9 over 2 times, this is about 3.284. So we have 2.236 plus 3.284 minus 2, which gives an area of approximately 3.520 square units. A key takeaway from this problem is recognizing the form of the integral for a circle. Knowing the standard result can save a lot of time and effort in an exam. And that concludes our walkthrough of Activity 5.1 from Mathematics N6. We've covered a variety of area calculation problems, each with its own unique challenges, from integrating with respect to y, to dealing with logarithms and exponentials, to sketching and finding intersection points for polynomials, and, finally, recognizing the area of a circular sector. Remember the key principles. Always sketch the graphs to visualize the area. Identify the upper and lower or right and left functions. Find the correct limits of integration, either given or by finding intersection points. And finally, set up and carefully evaluate the integral. Practice is essential to master these techniques. Try redoing these problems on your own, and then compare your answers. Don't be afraid to make mistakes. They are a valuable part of the learning process. Thank you for watching. If you found this tutorial helpful, please like and subscribe to Earthly Teachings to continue learning with us. Your support helps us create more clear and powerful learning content. See you in the next video.